lectures, and it's very pleasure to be on.
Thank you. So welcome back for the third and last lecture of this series on 1D systems. So today, last time we saw some nice properties like the charge fractionalization. So today I want to slowly move towards the problem that are hard to solve or simply unsolved. So I will give you a flavor of one problem where we go beyond this nice quadratic Hamiltonian that I've played with so far. And this is the example of the mod superfluid transition. So what does it mean? I consider a system of, let's say, bosons to fix the ID in the continuum, as we saw in the two last lectures. But now I will add a small periodic lattice, a small periodic potential, in addition to the, let's say, the continuum. And this is, of course, something that will couple to the density of particles. So I add simply a cosine potential here, which is produced, which can easily be produced in cold atoms by lasers, for example, and which tells that there are preferential positions that the system like to have, and so on. I will mostly consider the case of a weak lattice, but you can consider also a very deep lattice, in which cases you will go directly to Hubbard or Bose-Hubbard model, as we were discussing before. I will just, for convenience, discuss weak lattice. Okay. Now the question is, how do you treat such problem? Well, okay, you do what we started to see in the two last lecture. You use this dictionary, so you use the representation of the density that I showed you, and now you see that there is something which is, of course, interesting, is that the oscillation that comes from the periodic lattice here will cancel, or can potentially cancel, the oscillation that is coming in some of the terms that come from the density. So, in addition to the quadratic Hamiltonian, now you can eliminate these oscillations, provided that Q is equal to 2 pi rho 0, for example. So, if the periodicity of the potential you put corresponds exactly to 1 particle per minimum here, then this term will cancel exactly the oscillations you will get there. If you go to higher term in perturbation theories, you can also get the same effect if you have 1 particle every 2 sides, or 1 particle every 3 sides, and so on and so forth. But here I will concentrate on the case of 1 particle every side. So the case where Q is equal to 2 pi rho 0. So again, if it's not the case, then you have a term where you only partly cancel the oscillations. So you could say this cosine is still oscillating, so I throw it away, and I end up with my quadratic Hamiltonian, as before. But if I have Q which is equal to 2 pi rho 0, so if I have exactly 1 particle per side, then I have, in addition to the quadratic Hamiltonian, this term that will remain in the Hamiltonian. So I cannot deal purely with the quadratic Hamiltonian, but I have to deal with quadratic Hamiltonian plus this term. So this has a name, it's called the sine-Gordon Hamiltonian, and its properties are a priori very different from the one that are the one of the quadratic Hamiltonian. So first, let me make a little comment on what this term actually is able to do, because I think this is something which is important. So let me remind you, and this was mentioned this morning, that if you have a quantum state, which is an eigenstate, for example, of the position, and if you act with something which is exponential of I times the momentum conjugate to x, what you have done here is a translation of the state x, which is now becoming x plus a. Now, if you remember what the field phi is, the field phi, the gradient of the field phi, is up to a factor of pi, the momentum which is conjugate to the variable theta, the other variable. So if I apply an operator which is cosine 2 phi, which is exponential of I 2 phi, or exponential of minus I 2 phi, what I have applied is actually something which is exponential of IAP, but integrated from minus infinity to x. So I am making a translation of an eigenstate of variable theta by 2 pi for any position from minus infinity to the final point at which my operator is living, meaning my point x. And if I am at time tau, this is in space-time representation. It means that when I apply cosine of 2 phi on an eigenstate of the variable theta, I actually translate this eigenstate with a discontinuity here on this line from 0 here to 2 pi on the other side. Is it clear for everybody? Okay? So you notice that what this object is doing is that it's actually creating vortices where now the variable theta will turn by 2 pi when I go through this point, around this point, because I can spread now the discontinuity. Instead of making it brutal, I can make it smoother. So actually this is a vortex, this is an operator which will create vortices in the variable theta. So this is something which is quite remarkable in the sense that if I write this action here, which is my quadratic Hamiltonian as we were discussing in the variable theta, and if I look at this operator is actually the vortex creation operator in the variable theta. Now, if instead of action here, I was writing an Hamiltonian, and I was telling you this is something which creates vortices in the variable theta, is it an Hamiltonian that you have seen somewhere before? Maybe you have, maybe you haven't. So, I'm asking the question. No? Okay, so let's, instead of looking at the quantum problem, let's look at another problem. Let me go back here. Interesting. Okay. Don't ask me why it does this. And let me look at a problem which is the 2D classical XY model. So are you familiar with this model or not? Did you hear already the name somewhere? 2D classical XY model. So this is a very simple model. This is a model where you say on each side I have a little magnet, which is like a compass, which is of size 1. So each side has a spin, which is a classical spin, which is of size 1, so which I can represent by a cosine and a sine theta as a function of the coordinate x and y, if you want. And then I say that my spins interact with a very conventional Hamiltonian. Now I'm talking about the classical Hamiltonian. Now this is classical, which is minus j sum over nearest neighbor ij si scalar sj, which if I rewrite it in terms of the cosines is just minus j sum over nearest neighbor ij cosine theta I minus theta j. So essentially this Hamiltonian is if you want, a generalization of Ising model to the case where the spins, instead of being scalar variable, would be the simplest vector that you can imagine, which is a two-dimensional vector. Now the spatial dimension in which I stack the spin can be anything. It can be 1D, can be 2D, can be 3D, but the spins themselves, they are vectors which only live in the spin. Okay? So that's a very famous model, because, as I said, it's super simple, and that's the simplest model in which you have a continuous symmetry for the spins. Now, why am I talking about this Hamiltonian? Is because if I am very naive and if I say, oh, let me consider a configuration where all spins point practically in the same direction, I can consider that theta I minus theta j is small, in which case I will expand the cosine, and then I will write that my Hamiltonian, the cosine is 1 minus the argument square, so this would be j over 2, sum over ij nearest neighbor of theta I minus theta j squared. So this is of course not exact, this is an approximate solution. Now if I go to continuous limit, the difference of angle in two neighboring sides, I can consider that this is essentially I minus j, which is a vector if you want, times the gradient of the variable theta. So you see that I could rewrite this Hamiltonian essentially as, if I go to continuous, as sum over dx dy of a certain coefficient j tilde times grad x theta squared plus grad x theta, grad y theta squared. So the quadratic part that I have for my quantum problem looks very much to what I would have for this 2D xy model if I was considering that the time direction is like a second dimension. So this is one example of a canonical mapping that one can do between a d-dimensional quantum problem and a d+1 classical problem by using functional integral or by using simple identification. Very often you can map a d-dimensional quantum problem so in general it's in a d plus z classical problem, and I will explain in 1 second what z means. Z is, if you want, the number of dimensions of the time. Why can I say that time can have different number of dimensions than spatial? Well, imagine that I say I have a spectrum so that omega, the frequency, is behaving as k to the power alpha. K squared, for example. Well, it means that frequency is like inverse of time, and k is like inverse of length. So you see that from a scaling point of view, it means that time counts for more than one length. It counts as a length to the power alpha. So z depends on what is the spectrum of the quantum problem. So in general, you will map a quantum problem in d dimensions to a classical problem in d plus z dimension, where z is a function of your spectrum. So here alpha is actually what I call z. Okay? It's called the dynamical exponent. And for all problem or Luttinger liquid, because we have omega, which is u times k, z is equal to 1. But it's not general. You could have quantum problems for which z is equal to 2, or z equal 3, or z equal 1/4. So in general, this mapping is a little bit more common. Yeah?
Can this get corrections in an adjacent kind of z change?
So z is actually a non-trivial thing to compute in general. For the Luttinger liquid, because the theory is really Lorentz invariant, it's not renormalized. So the cosine will actually not renormalize this thing, because you see that the cosine is also with the sum of dx dy, so it has no reason to change the relation between x, dx d tau. There's no reason to change the scaling between x and tau. So if the theory is Lorentz invariant to start with, it will stay Lorentz invariant in the whole scaling. Now, why am I mentioning this problem? So what I would like to say is that my 1D problem resembles furiously to this 2D classical problem. But I have the cosine. So you could complain, where is the cosine going on? Well, the cosine is going on in the sense that this approximation for the 2D xy model, which consists in replacing the cosine in the 2D xy model here by the small angle expansion, is correct, but is correct up to configurations which contain vortices. So if I take a configuration where the spins are like this, this is a configuration for which I cannot do a small angle expansion and which are allowed in the original model. So actually, the 2D xy model is extremely famous because it has a very famous phase transition, which is known as the Berezinski-Kostelis-Thouless phase transition, and which was identified first by these three gentlemen, Berezinski, Kostelis, and Thouless, which consists in saying that if you look at the theory for this model, well, you cannot just expand the cosine stupidly, and you have to worry about vortex excitation. So here is a configuration of spin where you see vortices which have been represented. These are two vortices. This is an anti-vortex. So here the spin rotates here in this direction. Same thing here. The spin rotates in this direction. Sorry, I should be careful. So they rotate in this direction also. While here it's an anti-vortex. The spin rotates in the opposite direction. And you need to take into account this configuration if you want to understand the physics of the 2D XY model. This is a transition which is without an order parameter. The average of the spin is always 0. And actually, you can show that this 1D problem that I showed you is exactly mappable to the 2D XY model if you take into account the vortices. So this is a remarkable phase transition. For information. Okay, Berezinski unfortunately passed away, but Kostelis and Thouless got the Nobel Prize the same year than are they, because this is one example of topological excitations that are causing interesting physics in the system. Of course, people have tried to probe for this transition in atomic gases. There are very beautiful work, in particular in the group of Jean Dalibard, where he was trying to realize two-dimensional systems of bosons and using the phase of the bosons as the angle theta to realize the 2D XY model. So say I fix the amplitude of the wave function of the bosons, but there is a phase, which is like an angle, and I can realize the 2D XY model in 2D planes, which have been of atoms, which have been sliced by optical lattices in the system. If you want to know more on DKT, I can only recommend you this book, which is very nice. It has in particular a very nice historical introduction by Kostelis on the DKT transition itself. And it has to be pointed out that the book was edited before Kostelis and Thouless got the Nobel Prize, so I guess the editors had a good idea. Okay, so why am I mentioning this? Well, because actually we can study the Berezinski-Kostelis-Thouless transition either in the 2D language, but we can also study it in the 1D language by saying, okay, I have here something, this Hamiltonian should contain the seed of the DKT transition. So again, this Hamiltonian has for name the Sine-Gordon Hamiltonian, and it needs to be studied. So we can see immediately that there will be competition here between two types of term. This term likes to have the variable theta and phi. I remind you that this is grad phi, fluctuate. This term doesn't like the variable to fluctuate. It likes phi to be locked into the minima of the cosine. And the question is, who will win? So let me draw a little bit the consequence. I will rewrite the action in the more conventional way, which is the action in terms of phi. So the action will be something like 1 over k times the integral dx d tau of d tau phi square plus dx phi square. I've set u equal 1 just for simplicity, minus g cosine 2 phi. And you see exactly what happened. If I look at this, this is giving me a spectrum which is omega squared plus k squared. So this is a spectrum where omega is proportional to k. This is massless excitation. This means that I have gapless excitation. On the other hand, if the cosine wins, I should expand the cosine, and then I will have a spectrum which is omega squared plus k squared plus g times phi star q omega phi q omega. This is if I expand the cosine and I say this is g over 2 times 2 phi squared here. But then the spectrum is omega equals square root of k squared plus g, which means it has a gap. So I will have, depending on whether the cosine stays in my Hamiltonian, I will have a gap spectrum or I will have a massless spectrum. If it's purely quadratic, I have a massless spectrum. If the cosine wins, I will have a gapped spectrum. How to treat that? You do a renormalization group procedure where you vary the ultraviolet cutoff of the theory. It was explained by Eugene this morning. And you try to see how the coupling constants are evolving. So I will draw the RG procedure for you. So this can be drawn in the K and G plane. And there is a magic line here, which is the first diagonal. There is another magic line, which is the second diagonal. There is a magic value here, which is K equal 2. And then the flow goes as follows. If I start from a point which is here, it will flow here to a place where G is 0, so the cosine goes away, but there is a renormalized value of the Latinger parameter. If I start on the other side of this separatrix here, I will flow on the contrary to a region where the coupling is growing, and so this is gapped here. So you see that there is a transition where this region is completely different from the other side. This region is gapless, and therefore is a Tomonaga-Latinger liquid, as we discussed before. This other region is gapped, and it has the physics where you are with fermions, where you get exactly one particle per site in a lattice, if you want. And in a way, it tells you that if a particle was trying to move from one side to the next, it will pay a repulsion, and it prefers not to do that and to stay completely locked. This is an insulating phase. I mean, the Tomonaga-Latinger liquid is dominated by superfluid correlations. This other side is an insulator, and it has a name. It's called a Mott insulator, from Sir Neville Mott, who is the first person who understood that interaction could lead to an insulating phase. So if you want, here, if you imagine that the repulsion is super large, it's relatively easy to understand. If this particle was trying to move, it would have to go there, pay the repulsion, and it's very easy to see that now you would prefer to stay put. What is not easy to understand is that for a shallow lattice, this would also happen. If the lattice is super deep, that's very easy to understand, because you have only discrete position in which your particle can be. So it's the egg box again. If you have an egg box, you cannot put two eggs in the same minimum, because the repulsion between the eggs is too strong and the lattice is super deep. But here, note what this means. This means that if you're on this side, here, even an infinitesimal lattice, it doesn't matter if G is super small, it will always renormalize to large value. So it means that even a tiny, tiny lattice can immediately turn the system into an insulator. Of course, the gap will be super small, but the system will immediately turn into an insulator. So there is a magic value of K here, in which the system will turn from a superfluid to an insulator, even if the lattice is super small, which is highly non-obvious and definitely not true in more than one dimension. In more than one dimension, if you want a Mott insulator, you need a lattice which is deep. And you need strong repulsion. In 1D, you get a magic thing which happens, that provided the repulsion is strong enough, K is small enough, even an infinitesimal lattice can turn the system to be a Mott insulator. In the language of the XY model, this is the low temperature phase in which there are no vortices which are free, and this is the high temperature phase in which vortices unbind and completely scramble the spin correlation. Okay. But forget the XY model if you're not familiar with this, and let's just stick with the superfluid to insulator transition. So what it says is that as a function of K, If K is small, there will be a superfluid phase. Sorry, if K is large, there will be a superfluid phase. And if K is small, oops, K is small, and if this consent to erase, which for some reason it doesn't like to do, there will be a mot insulator. And the transition occurs, or should occur, exactly at K equal 2 if the lattice is super small.
Thierry, can you say again what the physical interaction, what the interactions are again? When K is smaller than 2, what that corresponds to physically to?
Some value of even a contact repulsion.
But just large?
Yeah, just larger than a certain magic value. I will show you the value in a second. But it's nothing special.
So it's
because non-interacting is K equal infinity for bosons, and infinite repulsion, the Tonks limit, is K equal 1. So you just increase the interaction, and then at some point you cross this magic value K equal 2. So it's nothing, it's just a number. It has no magic value of the interaction compared to the kinetic energy. It's interaction of the order of the kinetic energy. But nothing special for bosons. I will show you the thing in a moment.
So do you have to be for the without the lattice? Do you have to be in a Tonks regime already?
No, not yet.
Not yet.
Not yet. Not even.
Okay, not even. Okay.
Not even. No. You will reach that way before you are reaching the Tonks regime. It's something which happens somewhere in your way to the Tonks regime. Okay, so this is what I just said by writing the thing. There is a competition between this quadratic part and this part. You can view it if you like. You can view it if you like to think as phi as a space-time trajectory. You can imagine that phi has to move in this cosine potential. So there are two phases. There is a phase where the lines which are representing the space-time trajectories of phi can go from one minimum of the cosine to the next. And the phase where phi is locked in the minima is a phase where they would have to stay in the minimum of the cosine potential. But again, let's forget that. What you get is a Berezinski-Kosterlitz-Starless transition, which happened at K equal 2, and I'll come to the string order parameter after. Okay. As a result, we have this phase diagram. Here is the theoretical prediction. You can find more details, of course, in the reference I already gave you, where if you have exactly one boson per site, and you increase the interaction, you will go from a latical liquid to a Mott insulator, and there is a way to also induce the transition by doping the system, but I will not talk about this. This is a numerical simulation that were done by in the group of Steve White. Just to keep you awake, their convention for K is 1/k in my language, so don't be surprised if you see that the transition is exactly at 1/2 in their language, not 2. This is normal, but essentially it confirms very well the field theory, and of course the Mott insulator has a gap, which means that now the correlation function in the Mott insulator phase decreases exponentially and not as a power. So can one test this? And actually there were cold atoms are of course a fantastic place to test this, and there were early and beautiful experiments that were done in the group of Hans Christoph Nagel in Innsbruck, where he took bosons in the continuum, and he added a tiny potential, or tiny or big, because he can put whatever he wants. And then using a spectroscopic technique that I don't want to discuss, he tried to determine whether the system had a gap or no gap. So of course there is always, if the gap is too small you will not see it, but it allows you to decide where is the boundary. So here is the phase diagram. This is the lattice depth here. So 0 means of course no periodic lattice. And this parameter gamma is essentially, so this is 1/gamma, so this is essentially the repulsion between the bosons. So non-interacting bosons are somewhere there, and infinitely repulsive bosons, so the Tonks limit that Emmanuel was mentioning, would correspond here to gamma equals 0. Now if you look, you get a boundary between the superfluid and the Mott insulator, which clearly depends on the strength of the lattice. If the lattice is super high, you don't need that much repulsion to induce the Mott insulator. But you see that now when you lower, we started to play a little bit, and there are experiments in cold atoms, in particular using something called synthetic dimensions that I don't want to discuss too much. Here are experiments both from Jan Spielmann group in Maryland and from, again, the Florence group, Falani's group in Florence, where they realized ladders, so 3 couple chains, if you want, put a magnetic field, a fake magnetic field, and measure the population imbalance between the two, so they measure the whole. On the theoretical level, it's much more difficult to compute, so we have some attempts on the question. I won't go into the detail of the curve, I don't think it's important. Of course, if we try to do it for 2 chains and we cannot solve, it's even more difficult if I put many chains. We tried actually before to do many chains. It's super complicated because you need to go beyond the Tomonaga Oettinger liquid approximation. You need to take into account band curvature. Okay, never mind. It's quite complicated. So I don't want to pound and give you a whole list, my wish list of the problem I would love to solve, but I think I conveyed a little bit that there are at least a certain number of problems, which most of them have to do with coupling chains, with coupling one-dimensional degrees of freedom, that are still largely open and that we don't know how to solve. We are not the only one, sorry, just to say that. Here are 2 experiments on the same sample who measure the Hall effect. This experiment sees a very strong temperature dependence. This experiment sees something which is totally flat. Same sample, same temperature. At least one of these experiments is incorrect. So we cannot even say, you know, we take the experiment as a guide of what we should find theoretically. So this is what I would call really an open problem. So, sorry, so you had a question.
So in all these problems, can I say that if you solve the problems in free electrons, that would correspond to k equals 1,
yeah,
including all the band bending, you know.
Yeah, except if you solve the problem for k equal 1, you can expect it to be highly non-generic. Because again, in a 1D chain, k equal 1 has a behavior which is definitely non-generic. You keep quasi-particles, you don't get the decomposition into spin-on and holon, you don't have power laws with anomalous exponents, and so on and so forth. So what you would really like to solve is the problem with interactions. So, of course, the Hall effect without interaction, anybody can solve it in 5 minutes. And there are beautiful theories relating the Hall effect to chair numbers, so all these nice formulas which have been established in particular by Towles and Komoto, which work for non-interacting particles, we absolutely don't know how to extend them to interactions. So you're right, k equal 1 is one Oettinger liquid, but this Oettinger liquid has so specific properties that that's not what you would like to solve. Okay, I just finish here. I just hope that this tour of one-dimensional physics gave you a little idea of what one can do. I want the take-home message is that the Oettinger liquid theory is a framework to study this physics, but more importantly, to go way beyond. So it's not the end, it's the beginning. And what is important is that there are beautiful and challenging questions. We need an interplay of analytical and numerical technique to progress, and of course, especially new ideas. And what is even more important, there are many experimental realizations of such systems, both in condensed matter and in cold atoms, which makes it an exciting field. So on that, I shut up, and I thank you for your attention. So are there questions?
More questions.
Yeah.
So in Professor Schmidt's talk, we were also talking about impurities, and I think I must just be confused about when the results apply, but we were saying that the Anderson orthogonality catastrophe only occurs for the mass going to infinity. Is that only in higher dimension or something?
Yes. So in 1D, the recoil, the finite mass doesn't kill the Anderson orthogonality catastrophe, and that's of course one of the important differences. There are 2 important differences. One is the recoil, which doesn't kill the Anderson orthogonality catastrophe. And the second is if you say that the impurity is coupled to the density fluctuations of the solid, and you look at the modes for this density fluctuation of the mass, sorry, and you look at the spectral function, which is the density correlation as a function of Q and omega. Let's say the fermionic path, just for simplicity. In higher dimension, you would get a continuum of excitation, which is going from 0 to 2 kF, because you can do any excitation, take something here, bring it on another point of the Fermi surface at 0 cost in energy. In 1D, it's not correct, because the Fermi surface has only 2 points, so actually you lose this continuum here, and you get something which is with a hole here, if you want. There are no excitations available. So the fact that you get here a relatively sharply defined mode, contrarily to higher dimension, and the fact that the recoil doesn't keep the orthogonality catastrophe, makes this very specific behavior that I showed. Yeah.
Actually, as you said, there are many problems where you couple Luttinger liquids, which have not been solved. Do you think this is just like, okay, we understand the principles, it's just details that have to work out, or do you think there will be new paradigms that we will find?
I think there should be new paradigms, because
Okay.
I don't think it's details. Okay, there are technical details which prevent solving this problem, especially for fermions. I would say the bosons, one is in a much better shape if you just couple chains of bosons. And the reason is, okay, technically, is because when you couple this chain, first you get an horrible bunch of cosines that appear, so you get something like cosine phi on chain alpha minus phi on chain alpha plus 1, cosine theta on chain alpha minus theta on chain alpha plus 1, and we don't know what to do with these terms. That's the technical part. But already, by coupling single chains, you can see that there are in the quasi-1D regime very anomalous behavior. In the regime we can solve or control. Hall effect, for example, is weird. Transverse transport is weird, and very different from what you would get from a completely isotropic system. So I think the problem is hard, but also hides new physics in it, because the system has to remember that it came from an extremely strongly correlated system in 1D, so it cannot be a plain vanilla 3D Fermi. At least there will be extremely strongly dependent lifetime on the Fermi surface. There will be things which are remembering this 1D origin. So I don't know how new or important the paradigm will be, but I'm pretty sure they are.
So what about the usual RG? Why does it, I mean...
Oh, so the usual RG, I can tell you what you will find. You will find that the perpendicular hopping is a relevant perturbation with an exponent, which, okay, I don't want to, is something like k plus k minus 5, blah, blah. So it blows up, which means you flow to a regime which is not 1D anymore, which is not perturbatively controlled by a small t-perp anymore. And that's it. But since we only know how to establish the RG perturbatively, when you flow to strong coupling, you have to solve the strong coupling fixed point. And that's what we are unable to do. So the RG tells you that actually the system, for most systems of coupled chains, will not stay 1D anymore. Actually, there are some regimes in which they can stay 1D. And the RG helps you with that. But most of them, they simply flow away from the 1D. So the hopping is always, or practically always, a relevant perturbation. You can do RG, you can get the scale at which the system will stop to be 1D, and this scale is strongly renormalized compared to non-interacting system. It's not t-perp anymore. It's t-perp to a certain power, so you extract some information in that respect. But what is beyond, we don't know.
More questions? Remember, this is your last opportunity.
I'm here tomorrow.
Here it is.
If you have questions.